Okay, let's consider the following problem. Two masses, capital M, and this one. They are connected to a spring system. 1, 2, 3 springs. And here we define the x direction, that direction. So, let's find the equation of motion for each mass, this one and that one. And what does it mean, equation of motion? It means, in classical mechanics, introductory mechanics, it means that we are supposed to look at Newton's second law and see what that is telling us. And in order to do that, we need to find out the forces. So let's look at the left mass here and look at the forces. So what we can see here is that there is a damping force from this system. And if it goes that way, it will be a damping. Also, if it has a velocity in the other way, it will also be a damping. You know, if that is hold fixed, for example. And the program text tells us that the damping force is a constant b times the velocity, where the velocity is the relative velocity. What they mean is this velocity minus that velocity. And we can call that x dot x1 dot minus x2 dot. So we already know the size, the magnitude of the force is simply the constant b times this. Then they also say Fd, the damping force, opposes the motion. So what that means is, for example, if the mass here is moving to the right, has a speed to the right, then there will be a force to the left instead. And if that is moving to the left, then there will be a damping to the right, the damping force, opposing the motion, in other words. And if we're thinking a little bit about it, we can say that this force in the x direction equals minus b times the relative velocity here. And how can we realize that? Well, suppose, for example, that the speed, the velocity here at the second mass, x2 dot equals 0, and if x1 dot, the velocity, is positive, i.e. in the x direction, so if the velocity here is in that direction, then there must be a force in the other direction, opposing the motion, right? And you see here, if that is 0 and that is positive, then the force is negative. So that is in the velocity in the positive direction, but the force is in the negative direction, in the other direction. So it makes sense, and if the speed, the x1 dot, is in that direction, right, then it means that this is a negative number times another negative number is positive. So if it's in velocity in that direction, the force will be in the positive direction. So that is a formula that seems to work pretty well. So now we are going to think about the spring forces. What about the first spring? It's that one. Suppose its natural length is L naught. But now, when we move this a little bit, it's not L naught, it's L, a little bit larger, right? So L minus L naught. That, according to Hooke's law, should be the force times the spring constant K. But as you can see, if we extend this in that direction to L, L minus L naught, this total length then minus the natural length, that will be just a the variable x1. So that's what I say here. So the force is just this here is simply Hooke's law, and this is, from the variables that we are looking at, can be written minus kx1. And then the second spring. So the natural length is L0, but if we extend the spring, so then to, let's say, call that L2, right? Yeah, okay, L2. So L, it depends on what we're doing with x1 and x2. But one can realize if x1 is 0, then the new length L2 will be L0 plus x2. But if we let x1 increase, then we realize, then this distance decreases. So it must be L0 plus x2 minus x1. That is what I am writing here. And Hooke's law is what you see here. And L2 minus L0, what is that? X2 minus x1. So here you have the spring force for the second spring. And now let's look at the Newton's second law in the x direction. So what kind of force do we have? We have the spring force, let's use this one. And we have another spring force, use this one. And then we have the damping force, this one. And the sum of the forces in the x direction should be mass times acceleration in the x direction. So here is the first equation of motion. For what? For this mass. And a similar reasoning for the second mass will lead to a similar equation, like this, equation 2. Okay, and the next task is to introduce two new variables, y1 and y2, in the following fashion. y1, the sum of those variables, and here's the difference. And then you can find something rather interesting here. So because this equation here is depending on both x1 and x2 and this too, so it's a coupled differential equation here, which might be difficult to solve. So by using this trick here, we can decouple the equations, right? So for example, if we take equation 1 plus equation 2, you see this one plus this one, what is that? Minus k x1 plus x2, which is y1, so minus k y1. And if we take that term plus this, they cancel. That term plus this, they cancel. And then this plus this. But that's just mass times the acceleration y2. y1. So, wow, that's an incredible simplification, isn't it? Instead of using the variables x1 and x2, let's just use y1 instead. So you see this equation as it stands is just depending on one variable, y1, right? Through this trick. And similarly, if you take equation 1 minus equation 2, this term here minus this term here, it's this minus minus plus, and so on. You get this. And this turns out to be simplified to an equation that only depends on y2. That's just a fantastic simplification. Here, an equation only depending on y1, and here only on y2. That's fantastic. And this equation here, that's a damped harmonic oscillator where the variable is y2. And what I can say, for a damped differential equation, the solution will be damped down until the variable approaches 0. So in this case, for large times, the y2 variable here must approach 0. Right? And then, what is y2? that's x1 minus x2. So we know for large times x1 must be equal to x2. And let's call that x. So that's what this equation is about. And this one, yeah, you can see it's just the ordinary harmonic differential equation for a harmonic oscillator. So what do we know about that? We already learned that the solution is of type constant times cos like this. So y1 is this plus this. Okay, write that now. And the solution is of this type. A cosine omega t plus phi. And the omega is k over m square root. And then we got some initial condition in the problem text that from the beginning, both x1 and x2 is 0. Okay, so then the sum here is 0, not t equal 0. So if this is going to be 0, what you have is a cosine phi, and the solution is if phi equal pi half, then it's 0. So that's what you get here. And if it's pi half, then this cosine reduces to the sine function instead. So x1 plus x2 equal a sine omega t. And then problem text is telling us something about the velocity of point 1 at t equals 0. So let's differentiate this one. And what you get is this. And then, yeah, at t equals 0, that point, the left mass has the velocity v naught to the right, while the second mass, its velocity is 0. So what you have here then is v naught equal a omega, and cosine at t equals 0 is just 1. So, okay, we immediately find out now the amplitude here. That's v naught divided by omega. And at large times, those x1 and x2 must be equal. So then you have 2x, right? And the a is that. So you have, here's the amplitude, and sine omega t. So we have here, we have solved the problem simply. And they are, after a while in this stamp system, x1 and x2 will oscillate back and forth in phase. Thank you very much. That is the solution to this problem. Bye.